Hey guys, in this video we're going to take a look at section 11.8 on electron spin. This is a component of quantum mechanics. The details of it are a little hard to get your head around, at least they were for me. And so we're going to treat this in sort of a more classical way. But let's start at the beginning. So it was the early 1920s. A couple of physicists put together an experiment in which they uh, shot electrons out of this oven. Um, you may recall in J.J. Thomson's cookie dough model, he just heated up a coil and electrons came off of it, and he was able to shoot those electrons at a screen. This is a little bit similar in which this blue line here represents an electron gun, a stream of electrons coming out. What's different here is that Dr. Stern and Gerlach were using magnets, a north pole and a south pole. And what they expected to get, if the mechanics of Isaac Newton had been correct, is it would have been a solid line would have shown up on this screen here. What in fact happened is they got 2 points, one point of light right up here and one point of light right down here with nothing in between. And what this told them is that some of the electrons were attracted to let's say this is the North Pole, and went this way. The rest of the electrons were attracted to the South Pole and went this way, but none of the electrons were in between. And the takeaway from this is that electrons were behaving like tiny little magnets, and people wanted to find out why that was happening. So into the picture comes this guy named Wolfgang Pauli. There's a picture of him later in life. I think he was Austrian during World War II, or maybe just before World War II. He emigrated to the United States, where he worked at Princeton for a few years, but eventually he went back to Europe and he lived most of his life in Switzerland after that. And he could have a bit of an acerbic personality, but he was absolutely brilliant. He got his PhD in physics at the age of 21, for example. A little bit of a colorful character. He ended up marrying a cabaret dancer at one point in his life, although that didn't last particularly long. But one of the things Pauli suggested is that electrons are spinning. Now this is where you've got it gets a little tricky here, because when we think of spinning, we think of basketball spinning, or the earth spinning on its axis, or bowling balls rolling, and we're used to things that are spinning, right? But electrons aren't spinning that way. It's a different kind of spin. And so what most people do, is they say, look, I'm just going to pretend that the electrons are actually rotating around an axis, and that's going to make it easier for me to understand. And we do that even though we know that's not what's really happening. One of the reasons that doesn't make a lot of sense is that electrons are point particles, which means they don't have any volume. Or if they do, they don't have any volume that any experiments human beings have ever done have been able to measure, right? So something with no volume can't rotate around an axis. You need to have some volume for that idea to even make sense. But we're going to brush that under the chemistry rug, and we're going to pretend that electrons are in fact spinning. And one of the things that does is it makes electrons behave like magnets with a north pole and a south pole. And we represent that spin with this arrow. And so one of the things you're going to be seeing a lot from now on in this chapter of chemistry are arrows. And those arrows are indicating the direction that the electron is spinning. You could do this with your right hand, for example. If you take your right hand and you curl your fingers in the direction the yellow arrow is pointing, right? Curl your fingers like that. Your thumb is naturally going to point up in the direction that green arrow is pointing. That's sometimes called the right hand rule. But these arrows that you're going to start seeing represent electron spin. And so what this means is that you can have electrons spinning up if the arrow points up, or electrons can be spinning down if the electron points down. And I'm going to leave it at that, because for the purposes of chemistry, that's good enough. Now let's take a look at some new notation here. First of all, we're talking about helium. Helium has 2 electrons. This box represents the 1s orbital. You may recall that 1s orbital is the ground state. 1 means it has the least amount of energy. It's the smallest orbital. S means it's a spherical orbital. It's spherical in shape. We know that the 1s orbital can hold 2 electrons. Now, if you go back and you look at the section previous to this one, any s orbital can hold 2 electrons, and now we're in a position to understand why. One of those electrons is going to spin up, and the other electron is going to spin down. What's going on with that? Why can't they spin any direction they want? The reason has to do with the fact that, let's come back to this picture, the electrons are always negative. And what that means is that two like charges repel each other with a pretty strong electric force. That means these electrons want to get as far away from each other as possible. And what we're trying to do is cram both of them into this 1s orbital. Well, here's the thing. If they're spinning in opposite directions, this North Pole and this South Pole are going to attract each other. And down on this end, this South Pole and this North Pole are going to attract each other. That goes a certain way towards offsetting this electrical repulsion. So the idea here is that these arrows represent 2 electrons that do not want to be near each other. And by having them spin in opposite directions, we offset that repulsion just a little bit, right? If you want to talk about it in physics terms, you would say having the electrons spinning in opposite directions is more stable or is a lower energy state than if we had them spin in the same direction. So, anytime you've got a box, you get to put 1 electron up, 1 electron spin down. So let's look at carbon now. Carbon's a little more involved because it has 6 electrons. Well, the 1s orbital, the ground state, can hold 2 of those 6 electrons. One of them has to spin up, and then the other has to spin down. That's the minimum energy state. When I say minimum energy, that's like water flowing downhill. It's the way the electrons want to be arranged in the same way that water wants to flow downhill. Left to themselves, this is what they will spontaneously or naturally do. So where do we put the rest of the electrons? We've got 6 and we've only put 2 in so far. Well, we go to the next energy level, or we go to the next available orbital, and we'll take this apart in a little more detail in the next section. But for the time being, you'll have to take my word for it that the next energy level, sort of the first excited state, is this 2s. Again, s orbitals only consist of one box. These boxes are like sublevels. You can go back to the previous section. S orbitals always have one sublevel, p orbitals have 3 sublevels, d orbitals have 5 sublevels, and f orbitals have 7 sublevels. And each sublevel or box can hold 2 electrons, one spinning up, one spinning down. So with 1s and 2s, that accounts for 4 of our 6 electrons. Now we get to p. Since p orbitals can point in 3 different directions, there are 1, 2, 3 different sublevels. Right? Well, again, we want to make these electrons have the least amount of energy possible. Another way to say that, we want to let the electrons go where they naturally want to be. Well, they don't want to be together. They're negatively charged, and they want to get as far away from each other as they can. So if at all possible, each electron wants to be in its own sublevel. Each electron would prefer to be alone. And so if we can do that, then we put the electrons in all by themselves. And it's not that we are assigning the electrons to spaces. This is simply a notation that reflects what nature does spontaneously. And so the natural world, the universe, God, whatever you want to call it, plops 1 electron into this sublevel, 1 electron into this sublevel, and that one sits empty. What's all this business of spin good for, besides, making atoms that make up the universe and everything in it? Well, we're able to use this for a number of things, and this is one that you probably are familiar with. MRI stands for magnetic resonance imaging. So it takes advantage of the fact that these electrons are going to behave like tiny little magnets. Yeah. This is what the machine actually looks like. This is the business end of it right over here. It's got that donut shape because it consists of huge coils, I believe. There are big coils of probably copper wire in there, and there might even be a little bit of refrigerant to cool it down. What happens is if you run electricity through that copper, you can generate a pretty strong magnetic field. The more electricity you pump through that copper, the more or the stronger your electric. Okay, it'll make a sentence here. The more electricity that you pump through the copper wire, the stronger the magnetic field is going to be, and the more detail you'll get out of your MRI pictures. And I've included a few different ones here. Unfortunately, none of these are GIFs. Um, but you can see how it allows us to take slices of a person, not physical slices, but digital slices of a person. I don't understand enough about this to tell you what the different weighted means. Here's an extraordinary picture, presumably of a person's brain. It looks like there's a right and a left lobe or hemisphere there. And then here's a picture of a human heart in just stunning detail. What we're able to do with MRIs is really pretty remarkable. There are other applications, but they're not quite as common. If you end up in a physics or chemistry laboratory or research laboratory in industry, you might use them. But MRI is the one that you and I might end up encountering.